So today we will be starting with a new topic. Right, last week we had almost finished your data link layer. We had talked about your the functionality of your data link control, which was related to your flow and error control. Right, we discussed certain protocols and some numericals were there, which we will just given you to solve it. And one more functionality is there, which is your media access control. Maybe we'll just cover it sometime later. Now we'll start this week with your unit, with your third layer, the network layer. Right. So till now, when we were discussing about the OSI model, we'd seen that in your two layers, first layer is your physical layer, which is just responsible for your synchronization of the bits when you're placing it over your channel and how they will be travel from your sender to receiver. Right. Then we had come to your data link layer, which was responsible for encapsulating your encapsulation of your messages in frames, placing it on the channel, right? And for your basically it was dealing with your hop to hop delivery, right? From one node to the other, how it is going to move, right? Your data frame. So and also with every hop, your source and destination address will change, right? And here your address which was being used was your MAC or your physical address. So which is useful when we are within a local network, right? When you're traveling within your frame is traveling within the same local network, all the source and destination, if they are in the same network, right? Then in that case, your MAC address or physical address is going to will work fine when they're in the same network, right? And otherwise, when we're talking about your host to host delivery, right? When we have the source to destination, we have to deliver a packet where the source and destination are on different networks, right? They are not in the same network. Like one computer can be in one part of the world and you are trying to communicate with another computer which is on the other way, right? You usually see how these computers communicate. They communicate through the internet, right? What is the internet? Like you see your packets are traveling through, they'll be before reaching your destination computer, they will be traveling through several LANs and WANs, right? And each of them will be having their own some way to identify like which network you've entered, right? So for that we need a global addressing scheme, right? In that case, we need a global addressing scheme when we are talking about your uh, your your network layer, right? Where your source and destination can be totally different, far apart from each other, totally different networks, right? So for your source to destination delivery, the host to host delivery, computer delivery, which is done by your network layer, which is the responsibility of the network layer, you have to look for a global addressing schema, right? In that case, your MAC address or physical address will not be sufficient to identify your system, right? So for that case, because there are a number of things which are associated with your functionalities of your network layer, right? Because it is responsible for the delivery of the individual packets from the source to the destination host, right? And so we need some, and as I said, they will be traveling through different in internetworks, routers, switches. They will before reaching the final destination, right? So your network layer also needs to provide some routing mechanism so that uh, your uh, your packet reaches the destination, right? So all the routing for the routing mechanisms and for your source to destination delivery of a packet successful, it is very important that you need to identify your packets. You need to identify the source and destination addresses with the help of a global addressing scheme, which will be not limited just to your network but across the internet. And this global scheme is your IP address. This is one way to identify, right, your source and destination addresses across the globe. And this IP address is not just like it is unlike your MAC address, which is just a number, unique number which is being provided by the NIC. It follows a logical addressing way, right? It has a logical addressing way which helps to identify your frame uniquely and universally, right, across your globe, right, across the internet, right? So This first, when before we go forward with the functionalities of your network layer, first we need to understand your IP addressing, right? Which is, you for the time being you can understand it to be uniquely way to uniquely and universally identify your frame or your data packet. In that case, it is in your network layer, it is called a datagram across the globe, right? And this is the reason we because we are using this global addressing scheme, right, which is called your IP address. So all the protocol suite which we use in your network there, they are of belonging to your TCP IP protocol suite, right? So talking of your logical addressing, the first type of, there are two ways to identify, right, your data packets at your internet addresses, right? The current which is being used is your IPv4, right? This has a limitation in the sense that in this IPv4, the internet addresses are of 232 bits, which means that 32 bits means that only 2 to the power 32 addresses are provided, right? So if you need more addresses, then we have other design also of your IP layer, which is called your IPv6, right, which provides you 128-bit addresses and with much more flexibility in address allocation, right? And that we discuss maybe sometime later. But currently, which is being used by your IP TCP protocol suite is your IPv4 addressing. So, what is the use of this IPv4 addressing? It uniquely and universally defines the connection of a device to the internet. So, you see, whenever a device is connected to the internet, it is given a unique IP address. You must have seen. You can find the IP from the IP config command of your CMD. You can find the what is the IP address being assigned to that particular computer, right? This IPv4 address will help the computer to be identified across the globe, and this IP address has a it is not just any it is not just a number, right? It has a logical addressing way, right, where some part of your IP address forms your, because as I said, you'll be traveling across different networks, and networks also have certain hierarchies, and there'll be some networks within those networks and all, right? Today it has a proper logical addressing, right, which helps us to identify that not only your particular host, but that some part of your IP address also helps us to identify which network that particular address belongs to. We'll be studying how your IP address is what is the structure for it, how it is being used. So as I said, it is a 32-bit address, and this address universally and uniquely identifies it. So the address space which is provided by your IPv4 address is 2 to the power 32. That many systems can be identified at a time, right? So here first we will be understanding what is the notation for your IPv4 address. Your IPv4 address is in two notations. What are the two notations? One is your binary notation, where these bits, these 32 bits, are in the form of zeros and ones, and you can this 32 bits, when they are divided into blocks of 8 bits, right, and converted to their corresponding binary equivalent, right? So we have another notation called your dotted decimal notation, which is more prevalent, right? Dotted decimal notation is more understandable, right? Whenever you give the command of IP configs, it gives you your IP address in the form of your dotted decimal notation, right? And dotted notation, as I said, it is more compact and easier to read, and your internet addresses are usually written in this dotted decimal format. So simple 32 bits are there, which gives you an address space of 30 to the power 32. Sorry, to the power 32, right? And these 32 bits can be there in your binary notation in the IPv4 address, and the more prevalent and the more compact or easier form is your dotted decimal notation, where these 32 bits are divided into 8 bits blocks, and they're converted to their respective decimal equivalent, right? And this is the way how your internet identifies a particular host whenever it is connected to the internet, right? It is assigned an IP address, right? For that particular device is given, right? So there's a small numerical here. Nothing is there. You have to just simply convert it from your binary notation to your decimal dotted decimal notation. So as I said, you have to just place it in groups of 8 bits and you have to find the corresponding decimal equivalent. Right? You just go through it and conversely. What we can do is if you are given the dotted decimal, you can definitely find its binary equivalent by simply converting each of these in your decimal numbers into the respective octaves, right? So we are dividing your 32-bit address into octaves of 8 bits each, and these octaves are they combine to form your 32-bit IP address, right? Then next we come to the concept of classful addressing, right? What we did is initially when your IP addressing started, we had the concept of classes, right? Your internet architecture was based on your classful addressing, right? Even now this first bit forms a basis, so we're going to discuss it. But now the scheme is more or less obsolete, and we move towards the more rational addressing way, which is your classless addressing. Why we move to it, we're going to discuss that also. Right, what is happening in classful addressing is your 32-bit address space is divided into 5 classes, right? What we have to the part 32-bit address space is divided into 5 classes. What are these 5 classes? A, B, C, D, and E. All right, and whenever you're given an IP address, you can identify that which class your particular address belongs to. Whenever your IP address is given, if it is given in your binary notation, then if it starts with a 0, you can know that this particular address belongs to your class space of class A. If it is 2 bits, then if your first 2 bits are 10, then it is class B. If it is 110, it is class C. If it is your 3 times 1 0, it is D, otherwise it is 4 times 1 means class C. Similarly, all of these when converted into this corresponding dotted decimal notation have got the ranges. The class A addresses, right, they are the first byte or the first octet, right? It is in the range of 0 to 127. If your first octet or the first byte is in the range of 1 to 0 to 127, then it is belonging to class A. If it is from 120 to 191, then it is your class B. If it is in the range of 192 to 223, it is in class C. And in class D, it is 224 to 239, and class C, it is 240 to 255. Right, so whenever you're given an IP address, you can identify that to which class it belongs to. Another thing here is to note here is with your class 1 addressing, what you're doing, right? Each of this class is divided into a fixed number of blocks, right? Fixed number of blocks in the sense that if there is one large organization, right, which requires a block of addresses, right, it can be given an address from class in whenever an organization requests, it can be given from class A, B, or class C, right? But here, what is happening in class A? Class A addresses are used for large organizations, right? Large organizations here, how these classroom addressing works is that the in your class A, your first byte, this part is going to identify the network, and the remaining 3 octets they are going to define the they're going to map the host or the routers which are within that organization. So if you have a large organization, right, which requires a large number of IP addresses attached. There are a large number of hosts and routers within this organization. Then it is your class A addressing is designed for it, right? If you have a middle-sized organization, right, where you can just where the number of hosts and your routers, the number of hosts within your network. Okay, they are of middle size, say 10,000 or so. In that case, you can use a class B design. What is the class B design? Only the last two octets are going to identify. They are going to be used for identifying your host within the network, right? And if you have a very small organization, right, then your class C addressing is designed for it, because here only your last octet within this 32-bit address, only the last octet containing of 8 bits, 2 to the power 8. Okay, these many addresses can be used for identifying the host within the network. So in class A, you have your all 3 octets free, right? Your last 3 octets free to identify the host within the network, right? If you have a large organization with a large number of hosts within the network, then you go for class A design, right? If you have a middle-sized organization, then you go for class B, where your last two octets giving you 16 bits, that is 2 to the power 16 hosts within the network can be identified for it. Then comes your class C, which is for relatively very small organizations which are having just which just required within a network. They just need 2 to the power 8 hosts within that network, right? Attached host and routers, whatever it is, then they go for your class C addressing. Then, as I said, there is a flaw in your classful addressing. Why? Because if because where in if you see for class A, right, it is just too large to the power. If you're getting to the power 24 host, right, then it is too large for any organization, right? If you see the distribution of addresses, how it is in case of your class A, right, you have the number of blocks, right? The number of blocks are to the power of 7, right? Why? Because only the your 1 bit is restricted, the 1 bit 0 is going to show that it is a class address. The remaining 7 bits are used to identify the block, right? And within that block, in class A, what is happening? Your first octet is for the block, and the remaining 3 octets are going to identify the host within the block. So this is going to identify the block. And within this block, the 0 bit is fixed to identify it as your class C address. So remaining 7 bits are used to number of blocks which you can have within this for your class A designs are 2 to the power 7, which is equal to 128. And within these blocks, how many hosts you can have? Right, you can have 2 to the power of 24. Remaining 32 minus 8 bits, that is 24 bits, can be used for identifying the host within these blocks. So the block, a single block within a class A address is too large for any organization, right? That means your all of these addresses to the power 24, they might not be used. So in that case, your class A, most of the addresses are going to get wasted. Similarly, for class B also we have fixed for your classful addressing that how many bits will be required to identify the block and how many remaining bits are going to identify the host within the blocks. We have fixed it, right? So there is a limitation similarly for class B also. If class B, you have your 2 to the power 14. Why 14? Because you have got your 2 octets for class B. The 2 octets are going to be used for identifying the blocks within network. We're dividing a network into blocks. Within the blocks, we're placing your hosts within it, right? So here, since 2 bits are going to identify that it is a class B address, in this case, like 10 is going to identify the class B address. So remaining 16 minus 2, 14 bits to the power 14 are going to be used to identify the blocks, and remaining your 2 to the power 16 are going to identify the host within the blocks, right? So it may also be if an or middle sized organization received class B address, right, addressing scheme, that too may lead to uh, wastage of addresses, that too may be too large. Then it may go for class C, but in class C there is a limitation. What is the limitation? It might be too small for many organizations because only your 8 bits, the last octet, is available to identify the host within those, within a block, right? So here, since your address space, how it is divided into your 5 classes, and where your octets are going to be are fixed. Like in class A, your first octet is going to identify the block, and the remaining 24 bits are used to identify the host within the blocks, right? And in class B, it is fixed as your start. First two octets are going to identify the block, or you can say the network part, and the remaining 16 bits are going to identify the host within the network, right? So it is a possibility that and in class C only the last octet is available. So class C may be too small for any organization, because only 8 bits are available for identifying the host within the block, right? Then you may go for a class B addressing scheme, but that class B may be too large, right? Because you fixed it. So even though you do not require all 16 bits for identifying the host, it can lead to wastage of addresses. So class 1 addressing, right, where we had designed it in such a way that you had it was fixed that how many bits are going to be used for identifying the blocks and what are the bits that are going to be identifying the host within the blocks, could lead to a lot of wastage of addresses, right? Then one way to understand your your concept of classes and blocks is that in uh, in your classroom addressing, your IP address is divided into two parts. What are the two parts? Your net ID part and the host ID part, right? Where where what we were referring to as the number of blocks within class A, class B, class C, which actually represent your network ID, right? That there is a network here. Within that network, how many hosts are available? So in case of your class A, right, your network ID part, net ID part was your first byte. The first byte was used to identify your net ID, and the remaining 24 bits were used to identify your host ID part. For class B, it was your 2 bytes were used to identify your net ID part, and remaining 16 bits are going to identify the host within those blocks. Right, then you have your class C, right, where 3 bytes are there, which are going to define your net ID, and 1 byte is going to identify the host ID. Right, one way to represent it is in the form of your your masking mask, in the form of a mask, right? We this notation where you're going to use the default marks uh, for notation we're going to use for identifying the class for addressing, right? This is only going to give us an introduction how your concept of classless addressing came in, right? Which is also known as your this mask notation is also known as your CIDR notation, which is your classless interdomain routing notation. What is happening here is CP have got your 3 classes: class A, class B, class C, right? In if we write it in the form of a dotted decimal, how it can be written? As I said, in class A, right, the network ID part is your first byte, right? When use in we are dividing your address into the net ID and host ID part, right? Your the net ID part we represented by whatever bits you're using for representing net ID part, we are going to represent it by ones, and the number of bits which you're using for representing the host within that network ID, we are going to represent it by zeros, right? And when we are going to convert it to the dotted decimal notation, you know that all 8 ones, when they are converted to decimal part, they will be 255, and this will be 0.0.0. Another way to represent it is in the form of your CIDR notation, where /8 represents that your 8 bits, the starting 8 bits are going to be used for identifying the network ID. This /n, this n represents how many bits are going to represent the net ID, right? And your 32 minus n is going to represent your host ID part. So since your class A has got your first octet or your 8 bits, first 8 bits to represent your network ID, so we're going to represent it as /8. Right, in case of class B, you have your 16 bits for your network ID, so 16 bits /16, and for class C, you have your 3 octets, that makes your 24 bits, right? They're going to represent your network ID part, right? So then came the concept of, so this is one way to represent your classworks addressing with the help of your default mask, right? And this led to the default mask that we're using for classroom addressing. They gave us a concept of uh, classless addressing, where instead of having fixed number of traits, like for classing, the first byte is going to represent network ID, the remaining 3 octets are going to represent your host ID part, right? We can divide your address into address blocks, right? And the block size is, we can decide by a cell. The size of the block is based on the number of what do you, how many hosts you want to keep within it, right? So to get over this wastage of addresses which was happening in classful addressing, we start moving towards classless addressing. Okay. So in IPv4, when we're moving towards classless addressing, how a block of addresses here is identified, we have your IP address in the format x.y.z.t, right? And /n, the /n represents the mask. The mask tells, right, the starting n bits are going to represent the block, or you can say the network ID, and the remaining 32 minus n bits are going to represent the host within these blocks. So this wastage of addresses which was happening in classful addressing, it was overcome, right, with the help of your classless addressing, right, where a block of addresses can be given to an organization, and the size of the block is variable, right? It depends upon the number of hosts you want to keep within that block, right? And this led to the concept of your classless addressing, where it is not fixed that how many bits you want to keep for your uh, net ID and host ID part, but your /n notation helps us to identify, right, define the block of addresses we are going to assign. All right. And we're going to see some question on it, like how classless addressing can be used for identifying the addresses within a block of addresses. Suppose we are given a block of addresses being granted to a small organization, and one of the addresses here is your 205x.y.z.t /n. What n here is equal to? N is equal to 28, right? N equal to 28 means your starting 28 bits are going to represent your net ID, and the remaining 4 bits are going to represent your host ID part, right? We just solve the question here. Right? What is the, if you have to find the first address in the block, right? So how we can find it? If we convert it into your decimal, this decimal notation into its binary equivalent, right? It will be this, right? And as I said here, you're starting 28 bits. The starting 28 bits are going to represent your block or your net ID, and the remaining 4 bits are going to identify the host within this block, right? So if you have to find the first address in the block, the first address in the block can be found by setting the your last 4 bits, that is 32 minus 8 bits, the rightmost 4 bits to 0, right? So this is, if you convert it into its decimal equivalent, it will come to 205 or 637 or 32. All right. Here this is going to represent the first address, and this first address is used for identifying the block. Next, similarly, if you're going to find the last address belonging to this block, we're simply going to set here 32 minus n, that is your last 4 bits, that is your, if you take for this particular address equals slash 28, we set your last 4 bits, right, the rightmost 4 bits to all ones. This is going to represent the last address within this block, right? Because here again 28 bits are fixed. They are going to represent your net ID, and the remaining 4 bits are going to represent the host within the network. Right? So for your first address, what it will be, your 4 bits you set it to 0. This will represent the first address within the block. And for the last address, your last 4 bits are being set to 1. Right? That is going to represent the last address within the block. So in this way, if you are given slash n notation, or you say ADR notation, if you are given this information, if you're given an IP address and you're told that how many and its corresponding mask, we are given the slash n represents the mask. It tells us how many bits you're using for your net ID part, how many bits being used for your host ID part. We can find the first address, the last address, and the number of addresses. How many, the number of addresses in the block, how can we find? Number of addresses will be equal to how many bits you have being used for the host within that block, right? Since slash 28 means your 32 minus 28, which is equal to your last 4 bits, right? The 4 bits of your last octet, the last rightmost 4 bits, they are going to represent the addresses or the host within this particular block, right? With your 4 bits, you have to do the power 4, which is equal to 16, right? You can have number of addresses within this block are going to be 16. These many hosts you can have within this block, right? So if you're given an IP address and we are given the mask for it, we can find the first address, the last address, and the number of addresses within this block, right? Okay, another way to find, as I said, when we're finding the first address, simply we were putting the rightmost 4 bits as zeros. For the last address, we're putting the rightmost 4 bits as 1. And for the finding the number of addresses in the block, whenever your slash notation is given, your 32 minus n are going to represent the number of addresses within the block. Right? If we have to find, there's another way to find the first address, last address, and the number of addresses, right? Which is more used for in writing your programs and all, right? Whenever your IP address is given and corresponding mask is given. Like in this question, we had your mask as slash 28. If the mask, when it is converted into your binary notation, you can simply, what you can do, you can set the starting 28 bits as 1, right, and remaining 4 bits as zeros, right? And whatever address, if a single address of that particular block is given, you can find the first address by simply ANDing. We're doing the AND of these two of the bits of this of these two your when it is converted to the binary notation, you simply do the individual bits ANDing, right? The address which is given and the mask, which is when it is showed in your binary notation, when you're going to perform the AND of it, right? The uh, the result which you get is going to represent the false address. Then if you were to find the last address, as I said, last address, what does it mean? That your last four bits, in this case /28, it was using your 28 32 minus 20, that 4 bits will be used for your identifying the host within this block, right? So we can find it in this way also. If an address is given, you simply do the complement of the mask. Complement, what it will be? Your this now 28 bits will be 0 and the remaining last 4 bits will be 1. And now you perform your logical OR operation, right? OR means that if there are two ones, the result will be 1. If it is if like either of the cases there is a 1, you will get a 1, otherwise you will get a 0. Then you perform the logical or of the complement of the mask and any particular given address, and that will help you to find the last address. Right. So in this way, we see that how your mask notation is being used, where there was less wastage of addresses. Why there's less wastage of addresses? Because we have not fixed the net ID and host ID bits. Right? In classic addressing, what it was happening? It was fixed that your first octet or the starting 8 bits are going to represent the block or the net ID, and within that block, how many hosts you want to have, that used to be decided by the last 32 minus 8, that is your 24 bits, right? In class A case. Class B, what it was? It was 16 bits, 16 bits for net ID, 16 bits for host ID. So it was leading to wastage of addresses, right? Because it is not fixed, because here we're fixing it that how many bits we are going to keep for the host and the net ID part. So to avoid this wastage of addresses, we started moving towards your classless addressing, where your in your /n notation or the mask is being used to identify that how many, what is the size of your blocks depending upon the number of entities you want to keep within the block, right? In the mask notation, how it is in the form of x dot y dot z dot t, the IP address /n, the /n represents the number of n is your /n is your mask, and it represents like the n bits will be used to identify the net ID, right? And the remaining 32 minus n bits are going to represent your, going to identify your host within that network, right? So we will just end the class today here. Then we will be seeing some how your IPv4 hierarchy, two-level hierarchy is there, right? And where, as I said, your if you perform a two-level hierarchy, we're using /n notation. So your starting n bits are going to represent the network prefix, and the remaining 4 bits are going to identify the host within the network, right? And this complete 32 bits, where your n bits are for the network prefix, is going to represent the host address. We will see some questions on it in the next class. Just end the class today. Thank you.